So today I'm going to present some work that we are doing in my group at UCL. So this work is essentially a kind of preliminary work, but so we have already a paper out, that is coming out, and I will give you the reference later. So this is joint work with Matt Williams. Matt Williams was a postdoc in my group until recently. And essentially, today I'm going to talk about some ways of modeling spatio-temporal networks. And so the topic of this workshop was network science. So this is one line of work that we are following, and I think this was relevant for this workshop. So in terms of spatio-temporal system, we have many examples. Most of the real systems are spatio-temporal because they occupy clearly some space, and there are dynamics, so they are not static. So typical example is the London Underground that you see there. This is the network of the US domestic flights. So you see there is also the Hawaii Islands and Puerto Rico there. So, and you have a process over this network that essentially is the passenger transit. So we are interested, we started asking, so okay, we have this system, we are starting to ask some questions. So one possible question that is quite interesting is, what is the impact of failure in a system like that? This is a possible question that you can ask, but it's very interesting because one example is you can have various types of spatio-temporal system. One is the brain, and you can study, for example, the dynamics of cognitive processes on the brain. You can study problems if failures in the tube. For example, this is, if you are a commuter, you know very well that this is a big problem. This is a typical thing that you read every morning. So usually there is no service somewhere, and there is a problem that is a problem of delay. If you use the usual models of networks, most of the time you don't consider the problem of time. So they are not temporal networks. We did some work, like in the past 4 or 5 years, on temporal networks, but temporal networks don't essentially capture an important aspect that is, as I said, the space. So in this talk, I'm going to give you like a very, very quick introduction to the modeling, just a part of it, because I don't have time. And then the idea, or at least the intuition of spatio-temporal paths over networks. Then we are trying to discuss a bit about performances and robustnesses in these networks. So if you want to build a model of generalized spatio-temporal network, what we need clearly the fact that we need to represent spatial features. We need to potentially considering also mobile nodes. And this is quite interesting because essentially we would like a model that is very general, that is not able just to capture networks that are where the nodes are static, but also where nodes move. And this is very important if you want to model, for example, mobile networks. And this is like an area of big interest in my group. And the other aspect here is the dynamics and the fact that you might have delay in the interaction. For example, if you are traveling between London and Glasgow, you have a road there, so you have a spatial dimension, but you have also a delay in reaching the city. And this is important also to have a way that is generic and is also lossless in terms of information. And so if you want to represent a spatio-temporal network, we propose this model, essentially where you have, see there, nodes A and B, you have weights that are the delay over the links, and this delay represents the speed of interaction. And then you might have a propagation that essentially is constrained by the delay on the link. And essentially, you can have mobility in terms of nodes, so, and this is the mobile, the constraint in terms of mobile, constraint in terms of reachability in a sense. The other important thing is that if you have a process on this, because we want to capture also the process, what you need, essentially, if you have the classic temporal network that is representing over there, you will have that communication is instantaneous. Usually, temporal networks are represented as a sort of ensemble of graphs. And this ensemble of graphs essentially have also ordered. And what you have, essentially, you have the nodes that are reachable like a step T0 is A. If you start the process from A, typical example, you can consider an epidemics or information diffusion of these networks. Then you reach A, B, and D, and then you reach A, B, C, D, E. And then over there, you reach all the nodes. If you do the same down there, what you observe that you reach A, like in a spatio-temporal network, but then if the speed is 1 meter per time step that you see there, you reach only B, but you, at the same time, you are essentially in the middle of the edge. And this is something that is not captured in current models. And what we want to do is to try to capture this fact, that you are able to represent the fact that information is traveling over that edge. And then essentially you have the other cases, you reach a B again, but you see it is different. So like the real process that you have in the network is different. So there you are representing, if you are using a model like the one on the top, you are representing a process that is essentially not true. And then here A, B, C. Okay. This is it is a very simple observation. What we did essentially, we defined paths on these networks, and we try to consider this constraint propagation. So the problem is, as I said, that we have a propagation speed that essentially we don't want to reset every time the propagation of the message. So what we use a series of matrices. So one is the connectivity matrix. The other one is a distance matrix between the nodes. Then we have a speed matrices, that is the speed between the nodes. Again, it can be changed over time, because, for example, the traffic. And then we have something called progress matrix that capture essentially the fact that there you have just one step on that edge. Okay? So essentially there it will be one. The element of between in the matrix, the progress matrix between step 2, T1 to 2, will be 1. So essentially we will have these 4 matrices. Essentially this is a model for capturing also progress, not just adjacency, that is the connectivity, the distance, the speed, and the progress matrix. So this is like a representation. I will not give all the details that are in the paper, but I want just to introduce this model. So very simple model, but we are working on this because you can prove very interesting properties about this. Then you can define a spatio-temporal path where it is the usual definition of path, but you consider also the time of arrival in a certain node. So it's a sequence of nodes of successful node-to-node propagation. And this is the time of arrival at a certain vertex. The origin node, and then essentially you have all the nodes that you reach in your path. And essentially is the same like a temporal path, but what you can capture the delay. So you can capture the latency, you can capture the fact that there is a spatial length involved, and you capture also a sort of number of hops, because you can also see the number of hops here. And if you want to define a shortest spatio-temporal path, you consider both minimum latency and minimum spatial length. So if you want because this is a nice way of representing networks, but let's try to use this in a specific case. So let's assume that you want to measure the robustness of spatio-temporal networks. So we want to study, for example, essentially how system responds to node failure. And you can study with this type of model 3 aspects: topological, temporal, and spatial. And this is the interesting thing. At the same time, we consider as a vulnerability measures, we consider classic definition that you can find in the literature. So we consider temporal efficiency. Classic definition that I also don't like a lot of the notation, but this is the usual notation that you find in the literature. That is essentially temporal efficiency, that is the inverse, the sum and the inverse of the distances between nodes, and essentially the robustness, that is temporal robustness, essentially it is the efficiency, because the efficiency essentially measure the fact that you are able to reach the node, and you don't consider the distance, but the inverse of the distance, because if two nodes get disconnected, that value will be infinite otherwise. So the inverse will be 0, okay? So the temporal robustness, you consider essentially what happens if you have a certain percentage of failure, F, normalized by the case where you don't have any failure. So that is the notation that I don't like, but it's the notation that is used in the literature. So epsilon, where it is the case essentially where you don't have any failure. You can have this in terms of temporal efficiency. You can measure the distance, as I said, and you can consider also spatial efficiency and spatial robustness. Okay, this is the classic definition of spatial efficiency of efficiency or robustness. So we are interested in various performance. For example, the size of the classic measure, like the size of the giant component, the relative loss in temporal efficiency, and also the relative loss in spatial efficiency. So lower efficiency means that shortest path traverse longer distances. This is the most important bit that we have to remember here. So if you have 1, you have the same efficiency as in intact networks. If you have 0, all the nodes are disconnected. So this is the interesting thing that we want to see in the networks that we are going to study. So we consider at the moment 4 networks. So the London Underground, we used real data. So the nice thing of the London Underground that we get data like from the API of the London Transport, and you can get real-time data. So these are real-time data for 1 month. We got also real-time data for the same period of time for the US domestic flights, because there is Open Flights, that is a website where you can get all the data of the web of the flights. We also got some data, very interesting data about the C. elegans, that is another favorite of the biological community. So this is the Drosophila and the C. elegans, that is that nice worm. And the interesting thing is that we just didn't use the brain, essentially, when the worm is adult, but we consider the evolution of the brain over time from the egg to the adulthood. And these data are available. Especially, this is a very, very new data, and this is on openworld.org that was cited also yesterday. And what you can get really the evolution over time of the brain. And this is quite interesting because you can really see how the changes over time of the connectivity of the brain. And this is, and also we are studying also mobile networks, like Student Life Network, that is a network. So we consider in this case 22 Dartmouth students for 1 year. Essentially, we have information about collocation, calls, and SMSs and so on. So this is we have also other data set that we are using in terms of interaction that are quite interesting. But these are the first 4 that we have, and we have some result about them. So essentially, the interesting thing here is that the model represented is able to capture all these 4 cases. The most interesting thing probably is this fact that we have instantaneous propagation if you have a phone call, because you are calling directly with your friend, and instead you have very speed. This is the speed of the transmission, synaptic transmission, the C. elegans, and this is the median speed for the other network. Okay, and you have some nodes where the nodes are mobile or static, and vice versa. Topology can be time varying or not. Okay, so the first interesting thing that we want to see is what happens if you have random failure. Random failure, essentially, the resilience of the network underground to the random failure is pretty bad. But instead, what you see here, so this is, you have failure rate, spatial robustness, failure rate, giant component size, and so on. What you see if you have an increase of the failure rate, you see that the underground, essentially, in terms of the spatial case, so it is not essentially a robust network. Instead, the network, the most interesting thing probably is the communication, the flights and the sea elegance looks very optimized. And you can say, why? So then we start asking this kind of question, because you can also try to ask why. And essentially, the brain is optimized by evolution. So what you observe that it is extremely efficient. Also the brain of the human. We have also other previous work on the brain of the human. Is highly efficient compared to a random network because of the evolution. The flights is also quite efficient because essentially you can reroute. You have all the possible combination of the space. Really, it's space, but you can really change the routing of flights quite easily, and you can have redundancy. Actually, you want redundancy in your system. You have the alliances between among airlines for that reason as well, because you want redundancy in your system. Instead, the underground, the first underground was built in 1860, and it's very, very, very difficult to build a new line under London. So now a new line is coming up, the Crossrail, but it's extremely expensive. So you can't just say, okay, we reroute. And the other thing that is very, very interesting is that the London Underground is nothing else than a patchwork of independent rail lines that until the 1960s were different companies. So essentially it's a patchwork, and the patchwork is not optimized by definition. Okay, so this is interesting. We can see, I don't know how much time I have. How much do you have? Just to see. Okay. So the underground is highly fragile. So then we try to see if you can attack the network in the usual way, but we try to use the path between the centrality that essentially is given by the normalized number of paths or shortest path that go through that node. For example, the node V. In this case, it is the number of shortest path that go through it. And then we consider also the efficient centrality. Essentially, we consider the inverse of the distance. Okay. So we try to then the usual problem of the target attack. So if you have these essentially are the systematic attacks. We essentially want to target the nodes that support many shortest paths, and we want to target the node that allows fast information flow, spatially even. Okay. The problem is that if you want to study between, it is also the good thing. If you want to study between its efficiency, these are also the other one actually. These are extremely efficient attacks, but they require global knowledge of the network, and this is good in general because we will see later. But for example, the power grid is another case, and it's very difficult to attack the power grid, at least in the UK, because nobody really knows how it is built, because we have partial knowledge of the network. In Italy, it's very easy to disrupt the network, because it is known, it's even published, and it's very easy to target some nodes in the network. So is not something new. So we have various work on this. This is but here the spatial part is interesting. So it's interesting, especially if you consider the London Underground network. This is the map, the famous map of the London Underground network. What you see here is a network that is, as you know, topological, because if you want to go from so there is the same distance in this network. I don't know if I have the pointer, but between Yes. Okay. This one? Okay. Okay. So if you want to go between Covent Garden and Leicester Square, you see here it is the same distance between I Barnet and Colindale, and essentially this is 5 miles. This is like 300 meters. So this is clearly a topological network. And instead, the real network is this one, of the London Underground. So this is essentially we mapped the data that we have. So if you want to consider the real disruption, you should consider this network. The other one is not really really representative. So we try to do attacks also on this kind of network, and we saw as expected that the network, the London Underground network and the flight networks both have a decrease in terms of performance, and this is expected. But what happens for the flights network, you don't have this kind of phase transition in a sense, because, as we said, is a more robust network, and essentially is a more gentle disruption for the flight networks. Essentially, what happens with the London Underground network is that when you hit the core node that connect the peripheries, you disrupt the entire network. So it's sufficient to hit nodes that are connected to the peripheries, and then the network is essentially really disrupted. Instead, what you have in the flight networks, essentially, as I said, we have rerouting, possible rerouting in the network. And please note that we used directed network real data, so these are real data. Essentially, this is the real scenario. It's not that we are building a network without discarding information. This is real information using, so you have, this is the real rerouting. What I'm saying, that this is the real rerouting for flights. Okay. And then you can do the same thing for the robustness, as we said, and what we observe is this big disruption that happens, and again you see the same fact that you have more resilient, more smooth behavior for flights. Okay, similar degradation is resilient while the delay decreases. Okay. So, some summary of this talk. Essentially, I try to introduce, like very briefly, this model that we are studying. Essentially, this generalized spatio-temporal framework. This allows us for studying various aspects, topology, the classic work. Essentially, it's also very nice to see also what happens like against the classic work, and dynamics. Temporal networks, a lot of work in this area since 2000. Actually, it was like campus and Camber work. But you can also study space. So, and this is and delay. And this is important. It's very important for practical application. I showed 2 cases, but as I said, there is the brain that is another case that we are studying, and there is also this idea of information dissemination, and epidemiology is another big thing in this space. Very difficult to get reliable data. So, in fact, we try to be very conservative in this space. There are groups that are studying epidemics using also this mobile phone data in the small, but it's very difficult, in my opinion, to have reliable modeling because you don't observe all the actors in the network. Yes. Perfect. And as I said, so this kind of model allows to avoid oversimplification, and this is extremely important. So we don't have any loss of information, and this is important. And you can avoid also the problem of instantaneous transmission. And at the end, what we can do, we can also essentially to collapse process and structure in a single model. So this is the idea. we also show you some result about the attacks that are possible and what is possible to study with these attacks. So this is I show you like essentially experimental result, but another aspect is quite interesting, and I hope you also discuss with you later, is to study also potentially to prove some properties of these models. And essentially, I want to conclude with an example. So this is the case essentially when you close six tube stations at random, the temporal robustness is 94%. If you remember the tweet that I showed you at the beginning of the fact, essentially what happened that day was quite interesting. The tweet was about the flooding of Victoria's tube station. Essentially what happened that day, so there was a flooding of concrete. So they put the concrete in the wrong path and they flooded the tube with concrete. Yeah, it was not water. And yes, so and that day, because of the concrete, and it's not easy to remove the concrete, on the tracks, you had to close a branch of the Victoria line, and essentially these lines, when you close the station, you need to close also the other one because they are connected, because the trains that can go through it. So you have to close the sixth station, and the temporal robustness is 89%. And this is something that we didn't put in the paper because we think that is not okay. Might have implication. If you hit sixth station or in London using the betweenness efficiency attack that I showed you before, you disrupt the network enormously, and the temporal robustness is 32%, just with six stations. And these are the six stations that you can close. Essentially, are the stations that connect the peripheries. Okay. And this is quite interesting example. And here we're talking about disruption in terms of both delay and connectivity. So we are considering both. Is the interesting thing. We are considering both dimensions at the same time. Okay, so the take-home message is everything is a walking distance if you have time of the talk. And yes, and thanks for listening. The paper will appear probably this month in Royal Society Open Science. The paper is already available on archive, and if you are interested, you can find it there. And thanks. Finally, I would also say that we are launching in London also the Alan Turing Institute, and there will be programs for visitors and so on. So I suggest you to have a look at the website, the Alan Turing Institute. The Alan Turing Institute is the UK Data Science Institute. Okay, thanks for your attention. Yes.
Among your measures and, for instance, mean cut complexity of the network, or perhaps like some expansion properties, it seems to me from your robustness studies that the underground has got low crossing number is almost planar. So I would expect it to be much more easily partitionable than, for instance, you know.
Yes, in fact, I think that is a very interesting direction. We didn't study that, but when I said we can prove properties, I think that with this type of modeling, with also this progress metrics, you can try to discover new properties of this network that have not been studied before. Yes, I'm pretty sure there is some very interesting stuff there. And also, there have been some recent work from the SIAM at Strathclyde on properties of temporal network. I think you can expand that work, and you can see like it's a matrix analysis essentially, and you can try to expand that. And I think that is a nice direction. Well, let's start again. Yeah, thanks.